Good morning, Jonathan Rogers. My research area involved digital twin technology. The aim of my research was to determine if replacing information exchange processes with digital twin technology could A, improve building to operation information transfer, and B, improve the efficiency in the post-occupancy operational phase of BIM Level 2 projects in Ireland. My research objectives included a critical analysis of the Soft Landing Framework 2018, the REBA Plan of Work 2013, a comparison of actual and proposed building performance data, and a review of the BIM Level 2 information exchange requirements and deliverables. My research methodology included a literature review, interview questionnaires, an online survey, and development of a roadmap in accordance with BIM Level 2 deliverables. So a question I get asked a lot is, what is a digital twin? And this morning we've heard a lot of mentions about digital twin already. The term has become more common in the past few years. Gartner have identified digital twin as an emerging technology from 2017 to 2020. However, it is not a new concept. The concept was defined by NASA in the 1960s, where it was referred to as a mirrored system. It has become more widespread since approximately 2010, when it was associated with BIM and the Internet of Things. Digital twin seems to be the new buzzword relating to BIM for 2020. This year marked the first National Digital Twin Day, which was held on the 9th of September in London. So how do you define a digital twin? During my research, I've encountered multiple use cases, scenarios, and definitions relating to digital twin. This seems to have created a sense of confusion within the area. Some definitions I've encountered include a virtual model of a process, product, or service, the pairing of the virtual and physical worlds, a real-time digital representation of an object or system, and a virtual representation of a physical object or asset across its life cycle. Digital twins enable real-time monitoring and performance analysis. To create a digital twin, 3 elements are required: a physical object, a virtual representation of that object, and an interconnecting network of sensors providing real-time data and analysis. This is also referred to as the performance twin. Sensors connected to the building management system are graphically represented in a BIM environment such as Dash or 360. This version of a digital twin ensures that the virtual and physical versions are identical mirrors by providing bidirectional updating of data through a real-time data feed. So, is BIM classified as a digital twin? Many assets today are delivered using BIM in compliance with BIM Level 2. BIM Level 2 compliance requires alignment to international standards such as PAS 1192 and ISO 19650. One requirement of a digital twin is a physical asset. BIM enables the creation of a virtual representation of that physical asset. The first requirement of a digital twin involves the creation of a physical asset. A requirement of BIM Level 2 involves the exchange of information throughout the project. These information exchanges are also referred to as data drops. Data drops contain the following information relating to project stages, such as PDF documentation, including drawings, reports, and specifications, Excel spreadsheets, and IFC, which is an interoperable file format. These information deliverables contain static information. Static information is outdated information. Once this information is extracted from the model, it is out of date, as it does not represent as-built conditions. For a digital or performance twin to function, it requires bidirectional updating of data. Another requirement of BIM Level 2 is soft landings. Soft landings enable a smoother transition period following the construction to operational phase of a project. Some features of soft landings include a 3-year post-occupancy evaluation phase following building handover, a building performance evaluation to analyse building operational data. These evaluation methods are outdated, however. They involve manual methods of recording and analysing performance data, producing static information. To support my literature review, I developed interview questions relating to soft landings. The first question related to the familiarity of interview participants with soft landings. 100% of participants stated that they were familiar with soft landings. The second question related to the number of projects those participants worked on that provided soft landings. A third of participants didn't know, while the remainder, 67%, stated that the number of projects was between 0 and 20%. This was a low return for what is commonly referred to as a pillar of BIM. The second requirement of digital twin involves the creation of a virtual representation. In December 2018, the Centre of Digital Build Britain published the Gemini Principles, along with an interactive roadmap which was published in April 2019. These publications relate to the creation of a national digital twin. The Gemini Principles contain 3 categories with a total of 9 principles. Gemini Principle number 5 relates to openness and the creation of open, trustable data which is aligned to international standards relating to interoperability and classification. An example of classification is Uniclass 2015. Uniclass 2015 involves a series of codes related to the built environment. The creation of a national digital twin involves assigning Uniclass codes to buildings and building elements. This will ensure that all elements ranging from buildings to materials are coded and identifiable. These examples illustrate how the elements are identified using the classification codes and how the elements contained within the national digital twin are interlinked. To create openness, data needs to be standardized. Standardized and structured data enables the building management system to identify elements contained within the BIM models and the digital twin. To standardize data, it is vital that manufacturers structure their data through product data templates. Product data templates contain information relating to international definitions, performance certificates, standards, and product information. Standard data from product data templates is then used to create 3D components. These 3D components are now ready for use throughout the project design stages through to the building handover. Standardized data requires the creation of a common language. This is achieved through the implementation of digital data dictionaries. Digital data dictionaries enable the translation of common values with alternative meanings. An example is a value of measurement related to thermal performance. In Ireland and the UK, this is referred to as a U value. However, in Europe, this value is defined as thermal transmittance. To eliminate multiple definitions, digital data dictionaries identify the values and align the definitions. This ensures that the newly standardized data is accessible worldwide. The value from the digital data dictionaries can now be mapped to the product data templates. The final requirement of a digital twin involves linking the physical and virtual elements. This is achieved through linking the building management system to a connection of building sensors, enabling performance monitoring in real time through a live data feed. This combination produces dynamic information. This process is also referred to as Industry 4 or the Internet of Things. By the year 2020, it is estimated that there will be in the region of 20 to 50 billion connected devices. In April 2019, the world's population was 7.7 billion. That is an average of 4 to 7 connected devices per person in the world. As production levels for wireless sensors increases, mass production will lead to a reduction in cost, ensuring that the technology becomes more available. This will result in an increase in the opportunity to analyse dynamic information and building performance data. The combination of static and dynamic data leads to the creation of a cognitive environment. This can lead to preventative maintenance as the digital twin begins to adapt and react to its surroundings, learning from previous tasks and predicting when elements are scheduled for maintenance. The creation of a cognitive environment can also be used to monitor the performance of elements. The difference between actual building operational data against proposed design calculations is referred to as the performance gap. The creation of a cognitive environment can generate real-time data analysis, helping to address the issue of the performance gap through assessing real-time environmental conditions. With all the requirements for a digital twin, the data can now be visualized. This is made possible through Autodesk Dasher. Project Dasher began in 2009 as a research project by Autodesk. The aim was to develop visualization and analytical tools for building operations and information of things data in the context of building information models. Dasher is an open source program which is built on the Forge platform. The requirements for a Dasher project include as-built discipline models and real-time building data. Example projects involved in Dasher include 210 King Street, which is located in Toronto. This is the concept Dasher project of the Autodesk headquarters and was used as a demo model on the Dasher website until recently. The sensors were located on the desks on the 4th floor and throughout the building to record occupancy data. All the recorded data is visible and accessible in real time, leading to improved efficiency relating to building operations, reducing reduced costs and maintenance. Another example from Autodesk was the Pier 9 bridge project. This project was located in the Autodesk headquarters in San Francisco. A bridge within the building was used as a research project to record user load and occupancy levels. The research gained from the Pier 9 project was used to develop another bridge in collaboration with MX3D. MX3D are specialist designers based in Amsterdam who specialise in 3D metal printing. Lessons learned from the Pier 9 bridge project were applied to create a 3D printed bridge with inbuilt occupancy sensors. The data from the sensors was linked to Dasher and loading analysis calculations performed. The bridge was unveiled to the public at the Dutch Design Week in 2018, and members of the public were encouraged to use the bridge to record usage data. The bridge is planned to be located in Amsterdam after some final testing at the end of 2019, early 2020. And closer to home, an example of a functional digital twin has been developed by Autodesk, by Kingspan. This project was created in collaboration with Invicara and Autodesk. This is a clear example of the 3 requirements of a digital twin: a physical asset, a virtual representation, and performance data through sensors. The Icon Innovation Centre has been developed as an educational facility and as an innovative space to demonstrate Kingspan products and technologies. The ability to monitor buildings and building products can lead to better performance from products, leading to better performing buildings, resulting in better performing people. Following the development of the Icon Asset Information Model, a sensor housing prototype was designed and developed. Sensors located within the building include humidity, temperature, and motion. The sensors were represented within BIM by a sensor family and loaded into Dasher, and the information related to the sensors is available to link back to the Building Management System database. With data from the sensors, building performance data can now be analysed. There are multiple options available when analysing data. These options include humidity, temperature, and motion. The data received from the sensors can now be visualised within Dasher. As displayed, data can be divided in multiple variations, ranging from days to hours to minutes. By applying surface shading to the model, users can view readings and individual rooms and areas related within the building. The functionality of a performance twin can be enhanced with computational design. Computational design involves the creation of an automated workflow which results in the mass production of alternative options relating to a set series of definitions. This process is also referred to as generative design. There are 3 main elements required in the creation of a generative design. Creation of geometry through Revit, assessing and evaluating the design through Dynamo, and evolving and reviewing the outcomes through Refinery. The attached video displays an example of Refinery in action, cycling through the design goals and creating alternative options based on the scoring from the design goals. In order to create a generative design, 3 requirements are needed: input, output, and design goals. Design goals are the main driver behind the generative design process. An example of a generative design project is the Mars project, which is based in the Autodesk headquarters in Toronto. This contained a number of design goals including distraction, adjacency, views, and work style. These design goals led to the creation of multiple interior design options, resulting in a final design option that satisfied all design goals. Current methods of recording data for examinations, including LEED and BREEAM, can be improved. In the post-occupancy evaluation phase, building performance evaluation involves assessing manually recorded and collecting static data. Furthermore, assets require recertification after a 3-year period, requiring more manual data collection. Examples of some of these areas focused on during a BREEAM examination include visual comfort, air quality, and thermal comfort. By taking the static data recorded during examinations, we already have the basis of the design goals required to commence a generative design process. By identifying BREEAM examinations as design goals, we can utilise the data from previous projects as a base point for generative design of a new asset. This will ensure that future assets apply the lessons learned from previous projects and examination data. The creation of a cognitive environment can result in an opportunity to perform dynamic building performance analysis, helping to address the issue of the performance gap. So in conclusion, the combination of digital twin and Internet of Things have the potential to improve the performance of assets in the built environment. In order to do this, however, data needs to be structured and standardised, aligning with internationally recognised standards. To ensure that the physical and virtual assets remain mirrored, bidirectional updating of data is required. There was a limited response in relation to the number of projects providing soft landings information. This may be in relation to the technology being unable to process the data sufficiently. This can be resolved, however, by reusing data analysis from previous building analysis to form the basis for design goals for a generative design. Using digital twin in the post-occupancy phase can result in the identification of buildings which are found to be underperforming. The question is, what to do with these underperforming assets? The introduction of penalty clauses could be an option, but proof is going to be difficult using traditional methods. Monitoring the results of dynamic building analysis may be a solution for digital twin and Internet of Things, presenting an opportunity to introduce blockchain and smart contracts into the creation of new assets. And that's all from me. Thanks for taking the time to listen to me today and for CitA giving me the opportunity to present. There's my emails if you have questions for me, or we have a stand outside the door. My Kingsman colleague Martin Conlon is going to present after lunch a fully parametric detailing system called KingCAD Detailer. So that's it. Thanks for your time.